Okay, so I think this is actually the first lecture we've had recorded in like a week because we had power outages, exam reviews, exam previews, exams. So we haven't gone anywhere. We're still in object-oriented concepts. And I did in fact hit record. Excellent. Slides. So we're going to enter, we got a new vocabulary word today, just as a reminder where we were. Let's get to a little bit farther. A little farther. Oh, no, not that far. Loose and tight coupling. Right here. This is where I want to be. And let's see, does this work now? Ooh, okay, I'm happy. So we've got a new, can I now? Oh, excellent. So I can be over here. So we've got a new little tab, but of course I can't see, so I'm going to have to do something like this. And then we can kind of. Well, this is not for you right now. This is for the people later. So, like, I do a lot of this. Okay. All right. So, Harry Potter references will not be tolerated in this lecture. So we're going to just skip right over those. But we're going to talk about something called polymorphism. Polymorphism is related in many ways to inheritance. What is inheritance? Yes, when you inherit your fields and methods from your parent class. So here, what do we actually have? We've got a doggy, some sort of mallard, and a feline. When you give them commands, they all say different things, right? Woof, quack, meow. By the way, so people familiar with the song Zombie by the Cranberries? Okay. You know that's actually called the Goose song? If you've never heard the Goose song, you should listen to that, and you'll hear a goose featured prominently in there. Beside the point, though. So, is that Peter Pan? He looks very Peter Pan-like. Okay, so he says, now speak, and each animal responds with its own voice. So a polymorphism is the ability to take on more than one form, okay? And it's object-oriented in nature. Polymorphism, if you ever have an interview question about this, is using the parent class's interface to access child class implementations. Okay, so the idea of the three object classes, goose, dog, and cat, each having a method called speak. If speak is not doesn't belong to the individual subclasses, but belongs to a parent class, like animal. Animal has a method called speak, but dog and duck and cat, they change the meaning of speak. How many people are totally lost? Yes, excellent. That's where you should all be right now. It is not an easy concept to see, but hopefully with some examples, you'll see. Okay. The one other piece we need is we need a keyword abstract or virtual. That's how we tell when things are going to be polymorphic in nature. So, the whole point of this is we're going to have some reference variable that is of a parent class. For example, animal. We have some subclasses, duck, cat, and dog. Duck, cat, dog. They inherit from animal. Okay? We're going to refer to all of them by their base type, meaning we're going to refer to all of them as if they were animals, even though they're of type dog, of type cat, and of type Goose, duck, okay. So we're going to refer to all of them based on their interface. Now, I take this to an extreme. Okay, we know that cat inherits from animal, and maybe animal inherits from creature. We've had all these sort of sample classes before. The granddaddy of all objects is the object class itself. So if you have a list of objects, you can actually put anything into that list. Think about that for a second. Strings inherit from objects. Ints inherit from object. Everything inherits eventually from object. Now, what methods does object actually expose? Those are all three right there. ToString is what most of us think of. Now, most classes override toString. We did that with the fraction class in lab so that it would print out numerator / denominator. Okay, but every object has access to toString. It knows that toString exists. But each subclass defines its own custom behavior. That's what polymorphism is. We declare some method. For example, this method calculate surface. We were talking about this last class, right? We had a square and a circle, and we could calculate the surface area. So for some generic class, shape could define a virtual method, and virtual just means this class doesn't provide a final implementation. Other classes that inherit from this class will be able to change its behavior. So virtual means its behavior can be changed. Okay, and we've seen that because you have to use the override keyword to change the behavior of toString. Okay, if you go back and look at the fraction lab, it says void override toString. And that's because in object, toString is a virtual method or an abstract method. So once we use override, we can change the way that method works. You can't do it with certain things. You can't do it with static methods or other virtual methods. You also can't override anything willy-nilly. In order to use the override keyword, it has to be virtual or abstract in the parent class. Okay. So in the example from a few pages ago, okay, which one of these items is a parent class? Well, so there were two options. You presented the whole thing and the Peter Pan looking guy. The Peter Pan looking guy is not part of the hierarchy. In this case, the Peter Pan guy is like main. Okay, go ahead. A dog pictured class. Yeah, it's not up here. So there's a trick question. It's not up here. There are three classes: duck, dog, and cat. In order for polymorphism to work, these three classes have to inherit from some common ancestor. The common ancestor probably is animal or creature or something like that. Peter Pan is main, saying speak to a list of animals, not to a list of dogs, not to a list of cats or ducks, a list of animals. How many people are still lost? All right, at least you're up front about it. Let's go looking into some code, shall we? Move along here, doop, doop, doop. Here we've got a base class called figure. It's abstract. Abstract means that there are things inside of it that can be overridden. Overridden is a keyword, override. So it declares that there is a method called calculate surface. All figures have a surface area, so we can calculate the surface. And it returns, what data type does it return? It returns a double. Is calculate surface public or private? Public. The plus sign indicates public. Okay, then we have two other classes. Now, if one is called an abstract class, these down here are concrete classes. They actually can be instantiated. An abstract, you can't create an object that allocates memory of type figure. It doesn't exist. Okay, but you can inherit from figure, and so we inherit from figure to make square and circle, and they have slightly different parameters inside of them. They've got some sort of a location, and then either the size, the length of the side, or a radius. And they both override the parent class method, calculate surface. So here we've got calculate surface is size times size because it's a square. And over here, calculate the surface area of a circle, or the area. That's pi r squared. By the way, is this valid? Can we just say pi? What do we usually say? We say math.pi. You have to say, if you go up to the top of the program and say, using math, then everything will be put into your current namespace. So you could say pi if you're using math. Generally, we don't, because that puts a lot of stuff in your namespace. Pi, sine, all these other things. We don't want to do that. So this is the code. We've got a class figure. It's abstract. And it's got an abstract or a virtual method called calculate surface. And then two child classes. So the keys here, this class, since it has an abstract method, it has to be an abstract class. Two instances of the word abstract. It's abstract because it provides no implementation. There's no squiggly brackets with returns here. It's just semicolon. So we're saying, hey, this class has this method called calculate surface, but we're not telling you how to do it. And in fact, because it's abstract, you can't even make something of type figure. Yes? Virtual, you can provide a sample, a sample implementation that can fall back on. So abstract is like, it doesn't really exist at all. Virtual can provide a method. So, so down here in square, where's my mouse? In square, we can override the calculate surface and return something. So we can create items of type square. We say new square, that creates a square object. What's funny about that line where we create the square object, though? Where do we put square? Into what variable? We put it into F1, which is of type figure. You would think that that would cause some kind of a problem. You can't put strings into ints. You can't put ints into strings. They're different types. These two types, though, are related by a hierarchy. So this does something special. You can assign a child class object, so that's something that concrete and exists, to a parent class reference. Think about that sentence for a second, because that's the core of polymorphism. You can take some child object, like a duck, and you can assign it to a variable that's declared as an animal. And with that comes certain advantages and certain disadvantages. Okay? The next thing we say is f1.calculate surface area. Now, figure has no implementation for calculate surface area. So what code does this actually call? This F1 is a figure. Figure doesn't have an implementation. So does this throw a not implemented exception? Okay, you're shaking your head no. Where is it overridden? Yeah, it's declared as abstract inside a figure. No. F1 is type figure, but you're thinking along the right terms. It is a reference to a figure, but figures could be any kind of figure. It could be squares, circles, octagons, right? So when you say F1.calculate surface area, it does. Well, it's called late method binding. So at runtime, it says, hey, F1, what are you really? And it says, oh, I'm a square. And so figure says, well, that's lame. Get it? Because square. But square has an implementation, an overridden implementation for how to calculate its surface area using its internal state. I think that this is truly amazing. So a circle doesn't have a size. So if you tried to run this calculate surface area on this kind of object, you would crash because circle doesn't have a size. It has a radius. So it's smart enough to know, because it binds right before. So how many of you are in 263 or have taken 263? Okay, you understand that in assembly there's something called a call. It calls a function. It moves the program counter somewhere. Usually it's a fixed number. You call a label. Well, late method binding looks up what address to go to based on what type you actually are. This is all what polymorphism is. It's late binding of class inheritance. Okay, so here when we say calculate surface area with F1, okay, that calls the squares implementation of calculate surface area. And we're also going to have a figure F2 that's going to be a circle. Oh, maybe it's not a circle. F2 is a circle. So why does this say square? That's a typo. F2 we'll call the circle implementation. Let's scoot over to Visual Studio and just watch what happens here. Where's my mouse? Dropbox. Ching. Easy 264. Spring. Nope. Demos. This is cool, right? Moves the mouse and everything. It's shiny gold. What's not to like? Actually. Oh, I haven't even shown you the cool parts yet. All right, so here we are. Oh, but of course you can't see this, can you? So let's do that. So here's our polymorphism. Let's take a look at all these classes and how they relate. So we've got a circle, we've got a figure. Oh, you still can't see it. Why not? Better. Okay, so we've got this figure. It's an abstract class, and we've got a circle, and we've got a rectangle, and we've got a square. They all inherit from figure. Now, figure only provides this method, calculate surface area. The circle and the rectangle and the square, they all override calculate surface in about what you'd expect. I suspect you have, for the rectangle, height times width, pi r squared for the circle, and size squared. Where's the actual, oh, polymorphism. There it is. Hello? There it is. So, what do we do in the main program? We actually create a bunch of objects. We create a square, a circle, a rectangle, some more circles, two more squares, okay? And we're doing inline initialization. We say size is 3, radius is 2, width times height radius 3.5, all that. But the key feature is what type this array is. This is an array of figures. Now, it's possible to create an array of figures. What is not possible is to create a figure f equal to a new figure. That is illegal because it's an abstract class. So an abstract class can only exist in the abstract. The moment you try to create one, everything turns to dog do. You cannot create an instance of an abstract class. Okay? I could say new square. That's allowed. Or new circle or rectangle. That's allowed. Okay, figure can refer to things that are concrete subclasses. So a parent class reference can refer to concrete subclasses. So what do? I iterate over all of the figures and I print them out. Okay, all figures have a name and then they have a surface area. So what does the -9 mean? Yeah, left align 9. Josh. No. Yes, there is a reason not to do it. Because let's just look at rectangle for a second. Rectangle has a private width and height, a public constructor, and that's fine. What if I made these public properties? Because they are properties, right? Okay, build this. Everything builds and everything's fine, I hope. Oh, it's building like 18,000 properties. Yes, okay, it built. All other errors aside. Now, well, I need polymorphism.cs. So, what did I just do? Rectangle, right? Width and height. So if I say rectangle R equals new rectangle, does it not have a width equals 4, height equals 10. Oop. I can say R dot width equals 66. Compiles and it'll work, right? Now, figures sub 0, 1, 2. Figures sub 2 is also a rectangle, right? I know that that is a rectangle. But the only things that I have access to are calculate surface, equals, get hash code, get type, and toString. So most of those are from object, and the other is from the abstract class figures. So that is why you don't just make lists of objects, because you only have access to the parent class interface. So you only get calculate surface area. Now there's ways around this. If you treat it as a rectangle, you can say as. Figure 2 as a rectangle, dot width. Of course, you can do bad things. That compiles. But what is figure sub 1? It's a circle. Let's run that. Ooh, boy. Actually, that doesn't seem right. That's not the line I expected. Oh, no, that does make sense. Okay, so I tried to use the as keyword. Tried to treat it as a rectangle. That resulted in null. Okay, so that's sort of an opaque error message. It says null reference, object not set to an instance of an object. That's because you cannot do it as a null. But if I do figure sub 2, it didn't crash. I didn't print anything. So that's pretty cool. So I have my, where's my mouse? I have my surfaces all printed out here. They all, I assume, are correct. Moreover, it knows what type of figure it is, a square, a circle, a rectangle, okay? And it does that through the interface of objects. I can say figure.getType. So getType, hold on just a moment. I want to try something here. How many days ago did I try this? Oh. Hold that thought. Click, click. Nope. Yes. 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 Click. 7 seconds. 4. Okay, so can we talk about this for a second? How many people think they understand what polymorphism really means? They could explain it to me. How many people think they have no chance of explaining polymorphism to me? Okay. That's okay. How many people think they could explain what an abstract class is? Andrew, give it a try. You're on the fence.
So an abstract class would be a class that can't be realized but has something that can inherit.
Can't be realized is an important feature of an abstract class. It cannot be instantiated. Wonderful word, instantiated. Can't be instantiated. But it's got some stuff to give. What things can it give to us? A template that can be overridden. What's another word for a template that can be overridden? Something object-oriented in nature. A good vocabulary word. Starts with I. An interface. It provides us with an interface. That's right, that we can use. Pointer, magnify, digital laser, excellent, excellent. So it provides us with an interface, not necessarily an inheritable interface, but it provides us with abstract methods. Okay, so you can see that. You can see this. And you can see, nope, not that, not this, this, nope, this. Okay, now, you gonna function? Yes. That's what I wanted. Look at that. Yeah. Very good. Okay, so the reason I wanted to do this is because when you hover over, oh, I bet you this isn't going to work though now. Can I, oh, you can't. Sadness. I wanted to be able to zoom in on the fact that when you hover over getType returns a variable of type type. So the word type, capital T, Y-P-E, is a class. So even types are a class. But a type contains information about type. So if I say dot, I can get their base type if they inherit from things. the declaring method, the declaring type, the members of this type, the full name, all this stuff. In fact, this is a lot of what I used to grade certain parts of your exams. Okay, and so when we start talking about creating your own tests, I'm really just going to be referring to exam 1 because I had to do a lot of fun stuff to grade your exams using those tests. So in order to get the figure name, okay, I don't need that anymore. What? Yeah, we'll talk about how to deal with infinite loops in tests. So this figure right here is actually printing out a string because the get type returns a type object. The type object has a name property, which returns a string, and that string is what we saw here. So when I say square, that is a result of calling get type on the parent class reference. Remember, figure is of type figure. Okay, that figure is a type. So when I say .getType, it does some reflection and looks at the actual information on the heap, and it figures out that this is actually an instance of a square or a circle or a rectangle. So polymorphism is using the same brush to paint a bunch of different types of child objects. Yes?
So with get type, say you have the class creature, and then you have animal, mammal, dog, and the type you have is dog.
Yes.
You get type with the type become dog.
It would be dog. Then, but from that type variable would contain the base class of that. So from dog, you could go back to animal, to mammal, or whatever the order was. Dog, mammal, animal, creature. Okay. You could follow it up. Okay. But when you just call get type, it would give you dog. And if you said get type.name, it would be the string dog. Yes. Wouldn't compile. Yeah, well, let's try that, right? So here we are in circle. Instantly here, circle does not implement inherited abstract member. Meaning, if you are going to inherit from a circle class, you have to implement the if you're going to inherit from an abstract class, you have to implement all the abstract members unless, and this is something you can do, you can have part of your hierarchy be abstract several layers deep. So if you make this abstract, now everything is happy because you can, but then you can't create a circle. Yeah, no, you're going to get an error, right? Yeah, on the circles. Okay. So if you make something virtual, where do I want to be? I want to be in the figure. Nope. Here. Virtual. Okay. I have now provided an implementation. I don't think I can leave abstract out, but maybe I can. Okay, so technically virtual means it's not abstract. If I had one abstract member, the entire class would be abstract. So if there are any abstract members, the whole class is abstract. Now, let's make sure I'm saving all of this as I go along. Where is, polymorphism.cs. So now up here, this is legal. Okay? So if you declare something virtual, it can be overridden in the child class. Abstract means it must be implemented in the child class. So let's put a figure in here. Let's say new figure, comma. Okay, and we can run this, and the first thing it prints out will be a null reference exception. What did I... Oh, get rid of all this stuff. Okay, so it will print out a figure, and its surface area is 5. Not because it calculated any surface area, but because I said return 5. Now here's where things get interesting. It's virtual, so I don't have to override things in a child class. So now I have a circle, and I can give it a radius, but I don't have to override calculate surface area. So what happens now when I run this? Well, because there's no child implementation, where's my circles? All of my circles have an area of 5, regardless of their radius. Okay. Now also, you notice there's a few places where there's some printouts. If I go over to square, where are we? Oh, get out of here. Rectangle. Rectangle, especially because it actually says some things on the console. So not only does it calculate and return the width times the height, it prints out, hey, I called this version of calculate. In fact, you can go one step further and do this. So let's say you're happy with the virtual implementation of your parent class, but you want to do something extra like call circle. Okay, so here's figure. It's virtual now, and because it's virtual, we can say fig calc called. Every time we call calculate surface area on this figure, if it's a concrete version of this figure, it'll print out this. So let's look at what happens when we print. What I really care about is right here. This is the circle. So it prints out circle calc called, then it calls the base version. So the base version says figure calc called and returns 5. And then the main project now calls, it says prints circle surface area 5. Yes?
What would happen in the circle class? You replace overridden with
Nothing particularly interesting in this case. So actually, I'm not sure if you need to say virtual and override or virtual. What is it yelling at me? Yeah, so this, if you do just this, this isn't actually polymorphism because it's just hiding the other version. So if you do say virtual override, especially if you spell override correctly, oh no, okay, you can only do one or the other. So this is where some object-oriented languages differ from others. So if you say override, that overrides the old one. If you say virtual, it actually doesn't really help you all that much, okay? So if you made it virtual, you could then, in the child class of circle, override that, okay? So am I back to where I was? Override. Figure now has this and returns 5. Oh, okay, no. So I want to, okay, get rid of this. Put this back so it kind of works the way you'd expect it to work. Okay, so we have some child classes, a parent class, and we're referencing all of these objects through the lens of a figure. And we saw, you asked what's the disadvantage of using this? We only have access to what figure provides, and figure is only calculate surface area. All right, it's time for the poll. How many people are totally lost? You're totally lost? No? Adam, totally lost. You're college students. By definition, in the grand scheme of things, you're lost. So, no, about this particular topic of this particular class. All right. So we've talked about a couple of vocabulary words. We've talked about polymorphism. Poly, meaning many. Morphism, meaning form. Many forms. So a figure can take on many forms. Squares, circles, rectangles. That's why this metaphor works so well with these particular classes. Okay? But if you're going through a figure interface, you don't know if you're a square or a circle or a rectangle. So you can only calculate surface area. That's all a figure knows how to do. We can cast things. We can say figures sub-0 as some other type. But that could result in a null. So that's one danger there. We can say figure dot get type equals square. We can put that in and say if equals square. So that's one way of checking to see what we have here. Type of square. So we can compare types. We don't normally have to do this because you declare it as a type and it's going to be that type forever. But base classes might be pointing to child class implementations. So we can say if this is a square, print it was always going to be boop. It was always going to be boop. Calm yourself. Else, if figures sub-0 dot get type, and actually let's test figure type 1. Okay, so what is this code going to print out? Is it going to print out boop or bip? It's a variation on Bob. Well, what is figure sub 1? It's a square. So is it going to print boop or bip? It's going to print boop. Boop. Boop fig. Why did it print all smushed together like that? Because I used right, not right line. If I had changed this down here to right line, it would have. Okay, so we can compare things. So maybe if it's a certain type, we do a certain thing. We're doing out of time here. Okay, I'm going to scoot back to the. So as demos go, that is a really important demo. We tried a lot of things. Yes? An abstract field wouldn't really be a thing, right? Because it's not a thing. Properties can be abstract, I believe, but I'm not certain. Because they're really, they do some things, right? Is that an elephant with a monkey hand? No, that's an elephant with a monkey, orangutan hand coming out of it. Is that a hippo with an armadillo, a crocodile? And a panda with dog legs. I'm disturbed on so many levels. I also can't seem to find the... Where's... I don't want any of those. All right, hang on. This is not... start from current slide. Okay, there we go. Nope, slides. So we've done virtual, we've done override. Okay. So, what are you? Go back. Go back. Go back. Go back more. Stop there. Okay. That's funny because it did what I told it to do, so. So these are words that are not restricted to C++ or C# or F# or R. These are guiding principles, cohesion and coupling, not the BBC show. Cohesion describes how closely all the routines in a class or all the code in a routine support a central purpose. Cohesion is the stuff near other stuff relevant. Okay. We want strong cohesion in well-written code. Okay. What? No, not quite. When we create a class, well, actually, let's go back a bit. Let me ask you. When you create a function with a particular name like getNumber, what should that function do? Get the number. Should it do anything else? Not unless it says that it's going to do error checking. So if we did, just like in the exam, we had a get number and a force number. Get number tries to get a number and tells you if it failed or not. Force number gets you a number or it doesn't come back. Okay. So a class, similarly, should only do what it needs to do for a limited scope of work. Okay? The reason we try to make it like this is it makes it easier to manage our complexity. Some of you who have gone over pieces of the exam with have shown you if you had taken this bunch of code right here, turned it into a function, you would have made your overall code much simpler. Okay? Actually, go back to this for a second. Bad cohesion is code that you can't easily reuse because it needs a little bit from something over here, a little bit from something over here. So it doesn't stand on its own. Okay. Good cohesion to hard drive. Everything that you need to deal with for data storage, it's inside the box. Same with a CD-ROM, right? Everything to access the information stored on a CD-ROM is there. The laser, the motors that move the laser, the interface circuitry to talk to a SATA or an IDE. When you start having things that are difficult to pull apart, that's bad cohesion, and it's called spaghetti code. Spaghetti code is often easily recognized by looking at its cyclomatic complexity. Remember cyclomatic complexity? I'll put this on video for you guys who thought it was funny last time. What is cyclomatic complexity? Yeah, it's effectively the number of indents you have in your program. It's the number of levels of things. You want low cyclomatic complexity. Okay, typically if you have a zillion nested if statements, probably there's a better way of doing things. Did you have a question? Okay. So the math class, this is built-in class. It's got good cohesion. Everything you need to basically do any kind of standard math is in here, and nothing else. So we have sine functions and cosine functions, arcsine, so forth. But also in this math class, we have a constant, the most important constant with dealing with trigonometry, pi. We have pi, which is unrelated to spaghetti code, even though they're both foods. And we have exp, which does e to the something, something, something. And we also have the constant e. Yes? It doesn't. The up caret is an exclusive OR, a bitwise exclusive OR. If you tried to raise something to the second power by doing caret, run. Also, this has nothing to do with raising something to a power. This is e to something. If you want to raise something to a power, you need the pow block. Pow function. Pow function. Pow block is a different thing entirely. Okay. Let's look at some... no, I lied. We'll save bad examples of cohesion, and we'll talk about coupling to start next week.